Alright, let's work on the first problem of the day. This is going to be LeetCode number 105, construct binary tree from preorder and inorder traversal. Given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree, construct and return the binary tree. Okay. So let's think about the examples. So let's look at example 1 here. So we have 3, 9, 20, 15, and 7. And then we have 9, 3, 15, 20, and 7. So this is inorder. This is preorder. So this is left bias. Oh no. This is, I guess, print when traversing node. And this is print when, or print after left node traversal. I think a two pointers approach will probably work here. What I'm thinking is that we will take a look at the numbers within the preorder and inorder. If certain conditions hold, then we can create the node and the left right. What can we do here? Well, we know that the first node in preorder will be the root no matter what, because we assume that in preorder traversal we start from the root, because we print before we traverse the node. I believe preorder would be node left right. So assuming preorder is node left right, then the next node is on the left, or should be, and node after is on the right. Let me think. The main issue here is that we don't necessarily know if the tree has a bunch of nulls or not. So what does this do? Well, or what does the inorder traversal do? The inorder traversal has the opposite with node or left node right, which guarantees that the node to the right is the root, or the parent. So for example, this 9, we know that the parent is 3 because we go there next. And there cannot be a right side without a parent. So we know that the immediate right side is the parent. We can't just go to the right. Compare this to the preorder traversal where we go to the node. We don't know if this 9 is to the left or to the right. Right, because if the 9, let's say that this doesn't exist. This is just like not here. Well, it must be here because it's preorder traversal. But what if we did inorder like this? Yeah, there we go. So now we know that we don't know whether or not 3 is on the left or the right, or this 20 is on the left or the right. But we know that since this 15 is here, this 15 has a parent of 20, and the 7, in this case, because it's left node then right, then we know that this node has a parent on the left. But we only know that because 15 is a left, because we know that 15 is the left node, but we aren't guaranteed that 15 is a left node. And in fact, if we toss this together, well, if we remove this, then we don't know, then we don't have the ordering, right? We don't have left, root, right. Because if we had this 9 here, we can say left, root, right. Oh, it's not though. Let me think. In what case can we guarantee? Basically, the main question: in what cases of left and right pointers will we guarantee that some node is on the left, right of another? We know that the first node will be the root. Yeah, we said that already. Kind of looping back over what we did. But what do we know after that? The next node after the root node will either be on the left if it exists, else on the right. If after the first node, if the left and right pointers are the same, then we know that node is on the left. Because if this was a different number, then that would mean that because this is preorder and this is inorder, that when we decide to, if this inorder node is different, then that means that that value is all the way, that is the leaf node on the left hand side compared to this. Otherwise, that node's parent I think having left and right pointers is confusing because we're not dealing with it. That inorder's node's parent is the preorder. Is there a guarantee there? No, because if there are more layers than just 3, no, if more than 3 layers is false. Because if there are more than 3 layers, the inorder or the preorder will go first. Then it'll go left. Maybe rather than instead of doing that, then if the preorder's next is equal to inorder now, and this will be an else case, then we know that it is a parent. because then that guarantees that we have a parent node there. So for example, if we had a bunch of nodes like here, like 3, 9, then like 8 and like 10 or whatever here, and then finally, or like we had like a 10 and then like a 8 and then finally a 9, then we know that because preorder always checks the nodes that it visits first and then to the left. So 3, we know the left child is 10. We know the left child, or we think that the left child of that is going to be 8, or at least it should be. Left child of that is, and then because this preorder then goes to here, we know that 9 is some child of 8. We just don't know whether it's left or right. But in the case of Inorder, well, that doesn't tell us much about the direction of the node. That doesn't tell us much about whether or not that node is a left child or right child. We know that it is a child of that particular node, but we don't know whether or not it's on the left or the right. We know that preorder will favor itself and then its left child, but we don't know if there are any left children or if it's a right, or if this is a right child. Because in this case, it could be 3, then left child 10, left child 8. So it could be like, I could do 8, 10, 3, or 3, 10, 8, right? Because this is just preorder. So there's no guarantee that this 8 right here is the right child of 3. It could very well also, there could also be no node, no right child of 3, and thus the next one in the preorder traversal is going to be 8. Is it? I think so. Because if we did preorder, we would visit the node first, then it's left, then it's right. So we visit 3, then it's left, which is 10. Then it's left if it exists, which it doesn't. Or if it does exist, it's 8. So yeah, I don't think there's a guarantee there. Maybe there's a guarantee that we can get from the Inorder traversal. Right? Maybe there's a guarantee here that we can get. Well, if we know that the next number is 9, and we're currently at 9, then we know that this is the parent of this 9. How would it look in Inorder traversal? Well, we could check to see if this right number is next, right? Check if there exists number two away from Inorder now, and if that is after preorder, or after preorder next, then current is left child. That is right child. So the idea is that if we go here and we see a 15, and if that 15 happens to be next here, then we know that this 9 is a left child. Because we know that this preorder will go left, it'll go its own node first, then its left child, then its right child. And this one, it'll go the parent, or the left child, the node, and the right child. So if a right child exists, this should be the same as this. So 15 and 20 should be the same. Otherwise, would it be on the left? Would it be on the left side? Or, if some item exists over there, if some item exists after that 9, like in this case, I wish we had more examples to work with that wasn't this binary tree that's like pretty well filled. Well, maybe there are some additional insights that we can still draw from here. Let's see. Well, 3 and 9. We know that 3 is the parent of 9. What's the left, or what's on the left 2 spaces down from 9? That's 15. And since 15 is not equal to 20, we know that that this 15 is not a left pointer. Because they're not equal, we know that this 9... Can we guarantee and say that that 9 is a left pointer then? Well, if there was a left pointer there, well, what could this be? This could be left, or node left right, or node left, or node right. Then that current child is left child, that is right child. Otherwise, that next preorder is the right child. Does that mean that this 20 is going to be a child guaranteed? And in this space with the left node traversal, we have a bracket of 3. In terms of in order, it's usually left node right. But if we let's say that we didn't have any left nodes, then it'd just be node right and something else. Or it could be left node something else. Give me a second. Alright, so that was about 19 minutes. Let's go for another 11 minutes or so before we start taking a look at the solution. This preorder is naturally left node left right for preorder. The inner order is naturally left node right. Well, if we had left node right here, and left node right here, so this on the right, since it's not equal to this, that means you are on... That means you're on the right. Could it be... I think in that case it must be a node on the right. Maybe instead of doing something like a 2 pointers, maybe it's a sliding window of size 3. Then we check this. We see the node both happens to be 20. Left node happens to be 15 and right node happens to be 7. I wish I had a better example of like an imbalanced tree. Could I do something with this? Well, what would the inorder, or what would the preorder and inorders look like for this? The preorder would look like 3, 10, and 8. The inorder would look like 10, 3, and 8. Or we'll say A, B. So for A, the preorder would be 3, 10, and 8. And the inorder would be, because it's left always, so it's 8, 10, and then 3. Okay. And if it's balanced, then the preorder would be 3, 10, and 8. The same way. Except this is node left and left. But this is node left and right. Actually, preorder would be 10, 3, and then 8, right? No. Preorder is we visit the node as soon as we discover it. Okay. And then inorder would be 10, 3, and 8. This is node left, left. Well, how could we do something about this? What could we do about this? I think this window size 3 might work, but we also need to think about this is normally node left, right. So if this right doesn't match up with this right, then it doesn't make sense. But this will prioritize, this preorder will prioritize lower levels quicker. Whereas this Inorder one, actually I'm not sure if that's actually true. Cause this one would just go self, left, right. And this just goes left. Is there a situation where one of them could be completely out of whack? Like, if I had a larger tree as an example, that would be nice. If I had that, then the preorder for this would still stay the same, 3, 10, 8. But the inorder would be 9, 8, 7. This would be 3, 10, 8, then 9, 7. I think for preorder. Because this one is 3, 9, 20, 15, 7, yeah. Then in order it'd be 3, 8, 7, 10, 3. Or 9, 8, 7, 10, 3. Because it'd be left, the node itself, or its parent rather, then the right, then that node's parent, or the previous parent, and then that previous parent, or whatever's on the left. So in this case, there's not much that you can say by extracting the middle 3, or the consecutive 3 numbers, can you? Well, we don't know if 8 is on this, we don't know if 8 is on the left or the right. Let's see, preorder be 3. Then 10 is either on the left or the right. And then 8 could be in 4 places. And 2 squared. And that's the problem. Well, actually, it doesn't really matter, does it? So 8 could be in 4 places, but it doesn't matter. Should just be 2 choices anyways. It's either on the left of 10 or on the right of... it's either on the left of 10 or the right of 3. In terms of a preorder traversal. Yeah, I think this one is gonna be... This one is starting to just not... I'm really not getting anywhere with this, so... I think it's time to take a peek at the solution. God, this solution. Yeah, so I took a peek at the solution. Pretty much just took the Java solution and converted it to Kotlin. There's so much like there's so much required like intuition to like building up this solution that I don't even know where to grab, like where to draw from this well of creativity. So I guess the base intuitions aren't too bad, right? So the base intuition is that like it's something that I kind of got, and it's that the first element in the preorder traversal is going to be the root of our tree, but also all of these elements end up being roots within our preorder. They're either roots or they're leaves, right? But in any case, we can establish them as essentially roots of their own subtrees. And then we can build up a solution from there. Because once we know within the order, like let's say this 3, right? Well, we know that anything that within an in-order traversal, because it's, well, in order, that anything in its left subtree will be on the left, and anything on the right subtree will be on the right. That's just how it is. So once we find the index of that, we can build up a solution rooted at either the left or the right. The main, I guess, thing that didn't really click for me, and still didn't really click for me in terms of why it makes sense, is sort of the idea of, okay, well, we know that this has a left subtree, we know that this has a right subtree, but where is the root? We don't know where the root is. Well, we can go back to our preorder traversal, and if there is an element on the left, then we will visit that first. So therefore we build up the left subtree first, because that is the next element within our preorder traversal. Any element which is on the right subtree will be further down the line in this preorder list. So we build up basically the tree based on the roots, based on the rooting at the preorder, from the preorder traversal. So that's how we get the roots from the left and right subtrees. So for example, 3, we get the index at 1. Then we get the left subtree, which is somewhere within this area. Well, it only contains a 9, but pretend that it contains more elements. And we build up a right subtree, which contains these elements. We know that it contains those elements. We don't know for sure where the root is until we go back to our preorder traversal, because the root is the first thing within that subtree that we will traverse. The next, I guess the last thing to consider is, how do we know whether or not we have a left subtree or a right subtree? And the intuition here comes from the fact that we are splitting our array based on the left and right edges, in a very similar way to how we do binary search. Well, let's say, for example, that we recurse on this 9 right here, and we find that the index is at index 0. We will also set our right edge to this 0 as well, pretty much. Or actually, no, we'll set our right index. We'll set our right index to 1, and then from there, the idea is simply that if there exists a left subtree, we will recurse on it. If there are elements on the left, well, if we go in order, there should be elements on the left that we haven't traversed yet, as indicated by our left edge. There should be elements on the left that we have not traversed yet. Similar thing for the right side. So if our left edge is all the way up against our current root, then we know that there cannot exist a left subtree for this particular root. Very similar situation with the right subtree. Like I said, there is an insane amount of intuition, I think, in this problem in order to build up to the solution. And honestly, I'm not sure if I would have gotten it on my own, even if I had like a few more hours than the half an hour that I gave myself. But let's go ahead and submit it, and let's see if we actually got it, and if I actually translated the Java correctly. And it looks like we did. But yeah, so the main idea is that our preorder will go through, and our preorder is basically our list of roots. We can think of them as a list of roots, because within a preorder traversal, we will always visit the root of any tree first. We will, or at least add them to the list, right? And then we will go to the left subtree, and then to the right subtree. So that gives us our roots. Then, by looking at our Inorder traversal, we can determine what elements belong to the left and right subtrees of that root. We don't know exactly where the root of those left and right subtrees are, but we can deduce from our manipulation of the edges, as well as our preordered traversal again, whether or not a left subtree exists, as well as what the root is. Because if a left subtree exists, it will be indicated by our left and right edges, and we can determine the root because if a left subtree exists, then we will iterate over that root of the subtree first. So that's it for this problem. I hope you learned something, and I will see you for the next problem.